So today we will be studying about torsional couple per unit angular twist. So what is torsional couple per unit angular twist? First of all, we should know what is couple. Couple is moment of force. It is moment of force is called couple. Moment of force or torque. You know torque, that is R cross F. If F is the force and R is the distance about which the force is applied, that is called torque, which is also called moment of force or couple. So what is torsion? If you apply a torque to twist something, then it is called torsion. Torsion means twisting. So torsional couple is the torque which is used to twist is called torsional couple. So the angle by which the material is twisted is called angle of twist. So torsional couple per unit angular twist. Now to estimate the torsional couple per unit angular twist, let us consider a cylinder. Suppose this is a cylinder of length L. As you can see, this is a cylinder of length L and of radius. So this is the radius, say of R. R is the radius, and A and B is the axis of the cylinder. So L is the length of cylinder, R is its radius. Fine. Now AB is the axis of cylinder along L length. So AB is the axis. AB is the axis of the cylinder given by the dotted line. So AB is the axis, R is the radius, L is the length. Now suppose let us consider that the face C, to create a twist in this cylinder, what we have to do? We have to fix one face. So there are two flat faces, A and B. Now if you consider that face A, it is fixed. So it is fixed to a rigid support, and this B is free to twist. B is free to twist. Now let us consider a small elementary cylinder. This is the elementary cylinder. Say this is the elementary cylinder, say this is the of radius x. This is the radius, say x. Of radius x, and of thickness, this is the thickness say dx, and the length is same. So this is consider a small section of a cylinder which is a coaxial cylinder, and it is a hollow cylinder of length L, and radius is x, and radial thickness is dx. This will be clear here, as you can see. Suppose if we consider this is the cross section. If you look from, this is the point B. This is the smaller cylinder which you are taking. Fine. Now if this is the radius, total radius of the cylinder R, this is the radius of the elementary cylinder. There is the elementary hollow cylinder x. Its thickness is, this is the thickness. This thickness is dx. Now with this cylinder, if we consider if you consider a section, suppose this is a perpendicular line. Fine. Now as you can see, this is the perpendicular line between the surface A, which is fixed, and the surface B, which is free to move. Perpendicular line on the surface of the inner cylinder. So to make it clear, now see, this was the original cylinder, and it is a solid cylinder of length L and radius R. And this is the coaxial cylinder. This is the hollow cylinder. Now if we take this hollow cylinder as this one, so this is the same hollow cylinder, just for representation purpose. This is the fixed face A, this is the free face B. Now between these two faces, if we draw a perpendicular, suppose OP, O is a point in the face A, P is the point on the face B, and OP is the perpendicular to both this surface. Now if we apply a twisting couple, or that is the torque or a force, a tangential force, if we apply a tangential force, say here, this is the cross section, so you can see that, suppose this is the cross section of this cylinder. Now if we apply a force here, F, in a similar way, if we apply a force here, F is the force F on this elementary cylinder, then this force F and this force F will form a couple, and it will twist the cylinder. Now let us consider that this type of force will be acting in like this, in a cyclic way. Force will be acting in cyclic way. If we twist it in this way, now this line, you can see this line OP, because of this twist, the OP will move to OP dash. So in the cross section, as you can see this is B, this is P, so BP will move to BP dash. Here you see the BP will move to BP dash, making an angle theta. This angle theta is called angle of twist. Now as this moves with the application of this tangential force is tangential, with the application of tangential force, as it moves from P to P dash, the line BP moves to BP dash, and the line OP, as you can see, the line OP moves to OP dash. BP moves to BP dash, OP moves to OP dash. Now this angle by which the perpendicular is twisted, that perpendicular between the two faces is twisted, is given by angle psi. This is the angle psi. Now as you can see, this angle psi is actually called the shearing strain. It is the shearing strain. How it is the shearing strain? As you will see that as the angle theta, if the angle turned by the line OP perpendicular to the fixed and the free face after the application of tangential force, hence it is the shearing strain. How? As we can remember, suppose this is a face of a cube. Now if we apply a tangential force F here, this, suppose this is P, OP moves to OP dash. So this is OP moves to OP dash. Now for this, if we apply a tangential force F, then the shearing strain is phi. So when a perpendicular between a fixed face and a free face is turned by an angle, that angle is the shearing strain. Now as you can see that if we consider the applied force is F, if we consider that if applied force is F, if the applied force is F and the tangential stress T then modulus of rigidity is given by T by psi is given by T by phi. So T by phi is the stress, the tangential stress, and this is the shearing strain, and this is the modulus of rigidity. Also, as we know that the stress is given by force per unit area by psi is equal to force by area into this one. So by equating this, what we need to find the force applied. So what we will see that now as the eta was given by eta, the modulus of rigidity, the modulus of rigidity was given as force by area into phi, which implies force is equal to Na phi. So now what we have seen for this hollow cylinder, if you consider this is a hollow cylinder, the force is applied, suppose in this direction, force is applied in this direction, force is applied tangentially in this direction, and in opposite to it, say here. So this force is applied on which area? Tangential to which area? This area, fine. Now area of this, see, this is a hollow cylinder, so the cross section will be, this is the cross section of this one. So this is the x and this is dx. So what is the area? Total area is 2 pi x dx. 2 pi x is the length of this circle and dx is the thickness, so 2x into dx is the area, fine. Now what we will see that force is given by the force, tangential force acting on the hollow cylinder's free flat face B is F equal to n phi twice pi x dx. This is the area, So now after this we have to go to another discussion. So as we have found that see, this BP is turned to BP dash by an angle theta. In a similar way, with the application of the same tangential force, this OP is turned by an angle psi. Now as you can see, this angle psi, as you can see, this PP dash, it is the arc PP dash, the arc PP dash, arc is equal to radius into theta. So the radius is, this is what, this x, this radius is x, is equal to x into theta. is the x theta. Also you will see that the arc PP dash is also equal to L into phi, is also equal to L into phi. How? See, this PP dash is the same arc, and this is the angle, so this arc is equal to angle into radius. Fine. Now this relation you can write here. When P moves to P dash, OP moves to OP dash, and BP moves to BP dash. Fine. So arc PP dash, say you can see, take a triangle BPP dash. In triangle say BPP dash, the arc PP dash is equal to x into theta. Similarly, in triangle say OPP dash, the arc PP dash equal to L into psi. So using these two, what we can see, x theta equal to L phi, and phi is given by x by L into theta. Now as you can see, theta is fixed. If we consider this one, what we will see, that this is the phi, this is the angle theta. So theta is fixed and phi is a function of theta, because phi is equal to x theta by L. Now theta and L are fixed, so phi is a function of x. As you can see in this cylinder, if we use this cylinder, what you will see, that you will see that, see, if we decrease the x, suppose here it is x, if we decrease the x, the theta remains same, but if we decrease the x, and you will get from here that angle phi will reduce, because this PPT, this arc is reduced, so the x is reduced. So as you can see, as we move toward the axis of the cylinder, the x reduces, and as the x reduces, phi also reduces, and as we move toward the surface of the cylinder, the s becomes maximum, equal to the radius, the original radius of the solid cylinder r, and hence psi is also maximum. So the shearing strain is not constant but as function of x, which is the distance from the axis. Now as you see, this is the force equation, is the equation 1, the tangential force acting on the hollow cylinder, hollow cylinder's free face B, it is given by this one. This is the n by d is it is the n into strain into area, and the shearing strain is given by xl by theta. So using this 1 and 2 relation, what we will get, so 1 and 2 implies the force is given by n, instead of 5 we will write xl by theta twice pi x dx, it is equal to eta theta by L twice pi x square dx. So this is the expression for the force. Now what we need? Now we need to find, see, the tangential force is this one, but the factor which produces the twist is the torque applied, that is the couple of the force. So the moment of the force, the moment of the force or torque applied on the elementary hollow cylinder. What is the length? Length is L, radius is X, and thickness is dx. So for this cylinder, for the elementary cylinder, the moment of force or torque applied is given by d tau. Fine. So given by d tau about axis AB. As we see, this is the hollow cylinder. This is the dx, this is x. The force is applied in this direction, 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 see, like this, in anti-clockwise. Now because of this one has turned from P to, say, P dash. This is the angle theta. Now because of this turning, it produces a shearing strain phi in the perpendicular direction. So this is the BP, this is the BP. Now as you can see, this force, these forces are acting about this axis, perpendicular to the plane of the paper, and the distance from the axis to this point is, say, x. This is x plus dx, but you can take it, say, x is close to x plus dx. This is x. This is the distance, fine. So because of this, for this system, the torque is equal to, is given as r cross f. By definition, torque is r cross f. Fine. By definition, torque is r cross f. Here the r is the radial distance, there is the x, and the force is f. This, say, x cross f. You can write like this, which is, or you can directly write f into x, since f and x are perpendicular to each other. So sin theta is sin 90 equal to 1. So x cross f is equal to x f sin theta. Magnitude is f x f sin theta. So as this theta is 90 degree, this one is 1, this thing becomes 1, this thing becomes 1, is sin theta. So directly you can write d tau equal to fx, right here, since f and x are perpendicular to each other, because f is tangential and x is radius. So this d tau is f into x. So d tau is equal to, so f is, from the previous expression, theta L twice pi x square dx into x. So this d tau can be written as, d tau is equal to now n theta by L twice pi x cube dx. Fine, x cube dx. Now total torque acting on the face B of the cylinder. So total torque acting on the face B, or instead of face B you can write the fixed face, the free face. The cylinder can be obtained. How it can be obtained? Can be obtained by integrating the above expression between the limits. In the limits x equal to 0 to x equal to r. So this is the torque on the elementary cylinder. Now for total cylinder, we have to, what we have to do? So this is only the variable. The x is the variable. Now we have to change x from minimum to maximum. So the total torque is given by d tau. So d tau is eta twice pi eta theta by L x cube by dx, and x is changing from 0 to r. R is the radius of the solid cylinder. The cylinder for whose torsional couple we need to find is of radius r. Now this is given by twice pi eta theta by L. These are all constant. 0 to r x cube dx. So this x cube dx, what you can write, twice pi eta theta by L is x to the power 4 by 4, 0 to r, given by twice pi eta theta by L, r to the power 4, here you can take 4 common, r to the power 4 minus 0. Therefore torque is equal to, it is given by, the torque is given by this 2 and this one will cut, so it will give 2. So here torque is given by n pi theta r to the power 4 divided by twice L. So this is the torque. This is the torque, or called torsional couple. Now T is the torque, which is also called torsional couple. As we have discussed in the initial part of this video, that couple means moment of force or torque, and torsional couple means when the couple is used or torque is used to produce a twist, is called torsional couple. So torsional couple tau is given by T, the torsional couple. So if C is the torsional couple per unit angular twist, if C is the torsional couple per unit angular twist and T is the total torque, then torque is equal to, you can write like this, n pi r to the power 4 by twice L into theta. Therefore C is torsional couple per unit angle of twist, which is equal to n pi r to the power 4 divided by twice L. So this is what we what is called as torsional couple per unit twist, and couple divided by angle of twist. Fine. Now as you can see, this torsional couple per unit twist is equal and opposite. It is equal and opposite to the restoring couple per unit angular twist. Hence it is also called moment of torsion or torsional rigidity. Twist. Hence it is called moment of torsion. Moment of torsion or torsional rigidity. Fine. This is a definition. See why this C is restoring couple per unit twist. That means per unit twist. So tau is torsional couple, and also this tau is restoring couple. See, for shearing strain or any type of strain, what we have seen that when we apply a force to deform the body, a resisting force always acts, which is called a restoring force. So for a couple, if we apply a external couple, there will be a restoring couple to bring the body to its original configuration. So when we define some modulus of elasticity, we define it as the modulus of, then what do we always define in terms of resistance force. So here the restoring couple, that is the couple which wants to restore the cylinder into its original position, is actually equal to the applied couple, and hence this C is also known as the torsional rigidity or moment of torsion. I think this is clear now. Now just a quick revision. So for torsional couple per unit angular twist, what we need to apply a torsional couple to produce a angular twist. So let us consider a cylinder. Initially what we have to consider a solid cylinder of length L and radius R. After that we have taken a elementary cylinder of radius x and thickness dx of equal length L. Now what we have done, we have applied a force, tangential force along, and this is the fixed face, this one is fixed, and this is free to twist or free to move. Now what we have done, we have applied a tangential force, tangential couple. Actually couple means there will be, if there is a force in this direction, there is opposite force in other direction to make a twist. So when you twist this cylinder using a tangential force, what happened, it had created an angle of twist theta, and also the perpendicular direction, this perpendicular direction also produce angle phi, which is the shearing strain. Then what we have done, we have seen how this angle is the actually a shearing strain. After that what we have done, we have estimated the force applied in terms of modulus of rigidity. So as the modulus of here, the modulus of rigidity was given by the stress by strain. So from this we got what is the force. So the force was found to be the eta A and shearing strain. Now this area was the area of the hollow cylinder, not the actual solid cylinder. So from this the force was estimated. Also the relation between the angle of twist and shearing strain was estimated from the geometry. After that the relation was found that psi is equal to x L by theta. It was put in the force expression to find the force. Now our actual aim was to find the moment of force or the torque, the torsional torque. Now as initially what we have done, we have estimated the torque for the hollow cylinder. The torque was given by this expression. After that, to find the total torque, we have integrated the d tau such that the radius of the hollow cylinder changes from 0 to radius r. So after integration, what we have got, we got the total torque. Now as you can see, the total torque was also a function of theta. So if torque is this expression, so torque by theta, the torque by theta was given by eta pi r to the power 4 divided by twice L, which is defined as the torsional couple per unit angular twist, is given by this one. And later we have seen that this torsional couple per unit twist can also is equal to or can also be called as the restoring couple per unit twist, and hence it is also called moment of torsion or torsional rigidity. So we have found the torsional rigidity for a solid cylinder. Now if you consider a hollow cylinder, now for hollow cylinder, let R1 and R2 be the inner and outer radius. So R1 and R2 are the inner and outer radius of the cylinder of length L. Fine. So initial case the length was L, here also the length is L. There the radius was R, it was a solid cylinder. Here the radius is, inner radius is R1 and outer is R2. So it will be like this. Suppose say this is the cylinder. Now if this is the axis, this radius is R1 and this outer radius, this is suppose R2. Fine. This is solid, this shaded portion is are solid. Fine. And this portion is hollow. Now for such type of cylinder, what will be the torsional rigidity or torsional couple per unit twist? So internal radius is R1, is R2. Now suppose the torque is, total torque is T dash. If you consider that torsional couple acting on the face of the cylinder, on the free face of the cylinder be T tau. Then what happens? What we have to do? Then we have to is d tau. Fine. So if d tau dash was given by twice pi n theta by L x cube dx, this was the expression for that hollow cylinder, fine, of a thickness dx. Now the total torque, the torque of torsional couple is given by d tau dash, which is given by twice Now for the hollow cylinder, as this is the radius R1, inner radius, and this is the radius R2. Fine. Now for this system also, if we take a sectional, elemental thin hollow cylinder of radius, say x, of radius x, similar what we have taken for solid cylinder. Now for this elemental cylinder of radius x and length L, the d tau is given by twice by eta theta by L x cube dx, as in previous case. Now in order to get the total torque in the hollow cylinder, what we have to do? We have to take the integration of the d tau. So here in previous case for solid cylinder, what we have done? We have got for the solid cylinder, what we have done? We have integrated from x value of 0 to r. R was the radius of solid cylinder, because the minimum value of x was 0, maximum was r. But for the hollow cylinder, the x will run from smaller radius r1 to the external larger radius r2. So for the same formula, we will integrate from r1 to r2. After integrating, we will get x cube dx. It will be x to the power 4 by 4, and by putting the limit, we get twice by eta theta by 4l r2 4 r2 to the power 4 minus r1 to the power 4. So after simplification, we get this result. So this this tau dash is the torque, the torque produced in the hollow cylinder to produce a twist of theta. Now if C is the torsional couple, see, the torque is also known as a torsional couple, because this torque is producing a twist. So now that if C is the torsional couple per unit angular twist, then C dash is defined by tau dash by theta. So tau dash by theta will be this expression. Fine, this expression where R2 is the outer radius and R1 is the inner radius, with a condition R2 is greater than R1. So this C is also called as torsional rigidity. So this will be all. The difference was that we have taken the sectional cylinder for the solid cylinder and also for the hollow cylinder. Only the radius of the sectional cylinder runs from 0 to r in solid cylinder, and for hollow cylinder the x value runs from r1 to r2. This is pretty simple. So in the next, what we will do? We will compare the torsional rigidity, that is C or C tau of torsional rigidity of hollow and solid cylinder.